So we're going to approach what we're doing here today. We're going to approach it from two different ways. The first way is a way that I favor when it's a pretty simple situation. There are going to be other times when a little more of a structured approach is better. So I'm going to try to show you both here today. So for you two, like you would have thought of this as like substitution last year. Substitution, yeah. But what I want to do is point out, based on what the intro video was talking about, if you take this approach, you can become very fast. At these simple ones, you can do them super quick. And I guess you too, maybe Logan, you didn't hear about Timmy yet, did you?
What did Timmy do?
You're going to find out.
What do we have against Timmy?
He just is a fictitious character made up a long time ago, and he's endured through the years.
Could have been Johnny or Nick.
Could have been Peyton. You never know.
No, Peyton.
I'm just gonna, yeah.
So here's how you do this. Listen up now. Here's how you do this. You want to first recognize that your integrand is a clear composite, right? It's not just cosine of x or e to the x. Those are not composites. This one here, the input for cosine is not just an x, it's a 5x. So we call this composite. So this is what's going on in your head, and we'll get a little bit of this down on paper as well. But maybe you start off with this, and I'll just do a little rewrite here so I can give myself a little bit of room. Here's what's going on in your head. So I'm going to just try to write down maybe what you'd be thinking. Because remember, this can be fast. You'd say, you recognize this composite, and you'd say, all right, what is the inside function of the composite? So what would you say? What's the inside?
5x.
5x, right? So in your head, you're thinking the inside is 5x. And so then the next question is, what is the derivative of that inside? And what would you say?
5.
It's 5. So then, for this to work, for this reversed chain rule to work, because that's really what we're doing here, to truly reverse the chain rule, you have to answer this question, is the other factor, the one that's outside of your main composite, is the other factor a 5? Is your other factor a 5? And the answer is,
No.
what is it currently?
1.
It's a 1, right? It's 1 times cosine 5x. So what this means is, Timmy messed the chain rule up. He forgot to multiply by the derivative of the inside, didn't he?
No, he didn't.
Yes, he did. He totally forgot.
No, it didn't.
Because if he truly had done the chain rule, shouldn't there be a 5 right there?
Not necessarily.
Unless there was something there to cancel out.
Well, hang on.
And then pull out the 1.
This now perfectly fits the chain rule pattern, but you all know you can't just multiply an integrand by a 5 unless you balance it out by doing this.
1/5.
So what have I effectively multiplied this integral by? 1. But what I've done is I've changed the form of the inside so that it perfectly fits what should have been the chain rule. Timmy messed it up, we fixed it. But then I have balanced my fix by multiplying by 1/5, the reciprocal of my 5. Does that make sense? Now here's what happens. To finish this out, we fixed Timmy's issue. The 1/5 does not go anywhere because that's outside the antiderivative. The way this works then is you only find the antiderivative of the big outside function. So in this case, that'd be cosine. So what's the antiderivative of cosine? Sine, just positive sine. So sine of 5x and then plus c. And it's at this point that a lot of folks would justifiably ask the question, that's neat and everything, but where did the 5 go? And maybe where did the dx go?
Back in.
Didn't they show up as the result of a chain rule? So when you reverse it, they just go back into the input where they came from. So these two guys just go back in. They're just reintegrated back into the input. So they seem to have disappeared for no reason. The reason why they're disappearing is because they came from a chain rule, so when you reverse it, they go back to where they came from.
It's like closing a Pandora's box.
Sure, you are closing back up boxes. That's the illustration I for sure use in AB. I've got a question for you, though. What if you did this? What if you were like a little on the fence? You're like, I don't know if I want to do this whole Timmy messed up the chain rule thing. And I would like to check to see if my answer truly makes sense. What could I do?
Take the derivative.
Yes, just differentiate. So you could come over and check my answer. So to check my answer, I'd go d dx of 1/5 sine of 5x plus c. Well, the derivative of plus c would just be a 0, right? Because that's a constant term. And then I would say the derivative of sine is cosine, so this would be 1/5. I'll put a little equal sign in there. Be 1/5 times cosine of 5x. But we don't want to commit the same sin that Timmy did, right? We got to remember that that's a composite. And so what do you have to multiply by?
Times 5.
Times 5 because of the chain rule. The 5 and the 1/5 would cancel to be a 1, leaving us with our original integrand, hopefully confirming that we haven't messed this up, similar to what Timmy did.
Timmy just simplify.
That's crazy, man.
Timmy's a little.
No, the
Timmy's
5 was just missing. It's just gone.
Oh. Timmy's just a little.
There was no 5 there. I mean, we all make mistakes, right? Let's not get too judgmental, but... So, anyway, so
Isn't that mean the same?
I would like to just show you how fast this could be compared to a substitution process. I'm hoping that, maybe you guys will latch onto this, those that maybe haven't seen this before. Here's what I'm thinking. If I saw this on a quiz or a test, which I take your AP tests and stuff like that just to, just kind of for fun, to be honest. Here's what I would do. I'd look at this and say to myself, that's a composite. Is the derivative of the inside the other factor? Nope. So I would fix that and then adjust for my fix. I get 1/5 sine of 5x plus c, and I'm done. So instead of going through a whole substitution involving like the letter u or some other letter if you chose, I'm just going to do, in this case, a fairly simple one. I'm going to do the Timmy messed up the chain rule pattern and see if I can make that be accurate and also maybe a little quicker too. We're being silly with Timmy, but maybe you understand. I think you understand maybe the principle behind it as well. All right, so let's check out the next one, number 3. This might be a good opportunity for you to practice this. So there's this one. You might want to do a little rewrite on that radical before you did too much, but I think this is a nice one to be using. Timmy messed up the chain rule. The next 2 really are. So if you wanted to try number 3 and number 4, I think they're both nice examples. Set up well for this whole chain rule pattern, Timmy messing it up thing to work.
I genuinely don't remember that. I remember just closing my eyes and then opening my eyes and she's 10 feet away from me now on the ground.
Okay, let's look at number 3 and see how you did with this. Again, I feel like this is a more fairly basic composite setup here. So I would probably use the Timmy messed up the chain rule pattern procedure here. You could certainly use a substitution if you chose. If we were going to do the Timmy messed up the chain rule pattern thing, what is the inside of our composite?
X cubed plus 1.
X cubed plus 1. So it's right there. So in our heads, we're thinking, okay, there's the inside. We want to say, what's the derivative of that inside? Because we want the chain rule pattern to be there. So what is it?
You have to use this one. You forget it.
What's the derivative of the inside?
3x squared.
Thanks, Sam. Is the other factor 3x squared? It's just x squared. So Timmy blew it again. Ah, terrible. So we need to fix his issue. So we multiply that x squared by 3 so that it truly is the chain rule pattern. But you cannot do that unless you also multiply the outside by 1/3. And I want to say, I personally, honestly, I feel like this is a good shortcut, and this is why I'm showing this to you. Listen, please, Meg. Listen. The number one mistake that people make with this is they get lazy and they only put this number and they end up putting the wrong number. I would really encourage you to put the 3 where the 3 is supposed to be and then balance it out by putting the 1/3 instead of just saying, I'll mentally put this in and sort of maybe mentally put this other one in there. Just go 3, 1/3. It's really easy. This in and of itself is a shortcut. It's probably not a great idea to try to shortcut the shortcut. Just saying. So then once you discover that, once you have fixed Timmy's issue, then remember the 1/3 continues on down. It's going to be part of your antiderivative. And what happens to the 3x squared and the dx? They just drop right back into the input where they came from. And the only thing that really gets anti-differentiated is the big outside function, which is to the 1/2. So this is a power rule. So I'd go plus 1, and then I would divide by 3/2, aka multiply by 2/3. Don't forget your plus c. You get 2/9 times x cubed plus 1 to the 3/2 plus c. So far all the ones we've done could easily be done using a substitution. And if you did that, I got no problem with that. I would just want to show this to you. I'll show you substitution later as well. I don't know. Do you want to see it here? Maybe for our new folks, this would be good. So left side is Timmy messed it up. Right side is going to be substitution. So with substitution, the way you handle it is you say u equals the inside function. We often use the letter u. We're just going to use this to help us simplify our integrand. You always have to find the du, the differential, to go with this. So we would say that du dx equals 3x squared. Therefore, du equals 3x squared dx. We're always going to be finding that. And we'll do an official substitution here in a little bit, in one case where you kind of have to do it. And then what you do is you try to substitute into your integrand. So I'm going to start off with this, and I'll substitute into it. And I'll say that square root of x cubed plus 1 could just be u to the 1/2, right? And then x squared, still in there. But then we're always going to be substituting our dx out of there. So do you guys see anything I could use to substitute in for dx? There's a du, but it wouldn't just be du, it would be du.
Or divided by
Yeah, we have to divide over here by 3x squared to get the appropriate substitution relationship set up. So dx equals du over 3x squared. And then maybe you see it, something's going to cancel here, right? The x squared, so they cancel out of there. So the x squareds cancel. So you end up with,
We did it way differently.
Really? What do you do?
We would just do 1/3 on the outside of the integrand and then put du in and not do it.
Oh, how'd you figure out 1/3?
well, check this out.
Like if you multiply 1/3 times du, it would be x squared dx.
Sure,
X squared
that's
dx.
you just said we did it way different. I mean, honestly,
I mean, it's the same thing.
is that
but we just,
way
like,
different?
didn't Do the whole that.
I think that's highly debatable as to the degree of difference there.
You know,
Yeah,
I don't want to get in an argument right now.
I pulled out the 1/3 one step after you did.
I would literally cry.
Anyways, so then, well, obviously we're not done yet. So let's see here. Where do I have room? So it'd be 1/3 times 2/3 u to the 3/2 plus c. And then you'd still need to plug back in your u. So it'd be 2/9 times x cubed plus 1 to the 3/2 plus c. What is the what?
I just can't see it.
I'm sorry, it just got jammed up in there. This is actually making my point for me. I feel like on these simpler integrands, Timmy messing up the chain rule doesn't take up very much space, and it's quick, whereas the substitution, which we'll do more of the substitution,
Takes a while.
takes a little more space and a little longer time.
2/3 u to middle.
Right, so it's the same antiderivative, you just have a u, and then you got to plug back in the x cubed plus 1. Anyways, just a little comparison. Hey, if you haven't already looked at number 4, please do that. I'll give you just another couple minutes here to try number 4, for those that didn't get all the way to that. And again, I feel like this one is set up nicely for the Timmy messed up the chain rule pattern, although feel free to use u substitution if that's what you feel like is better.
Not vanilla bean frozen yogurt.
I thought
I was gonna say, oh boy, that went 0 to 100 real quick.
Got really emotional over ice cream there. Interesting.
I just love
Okay, so Timmy messed it up. By what factor did Timmy mess this up? By a 2. So if we fix his chain rule mistake by multiplying the outside factor by 2, we also have to multiply the outside of the integral by 1/2. So as we try to wrap this one up, the 1/2 does not go anywhere. The 2x and the dx are just going to be reintegrated back into the input. And the only thing we really are going to be anti-differentiating is the outside, which in this case is the exponent again. So what would the new exponent be? 2/3. That's right. And we'd also multiply by the reciprocal of that, or divide by it, however you want to look at that. So it'd be times 3/2. So I'm coming up with 3/4 times that. X squared plus 1 to the 2/3 plus c.
Yes.
Okay. There's one last one. Again, I want to give you a moment to try to process through that one. This one is going to, it involves a fraction, right? Am I remembering this right?
Yeah.
Yeah. So just maybe as an aid to everyone, especially our new folks, we, up until our next unit, we're going to avoid dealing with fractions as much as possible. And so I think this is no different. We're not going to tackle this fraction head on. We're going to manipulate it by moving the denominator up and dealing with the exponent. And then once you've done that, it'll be pretty nicely set up for Timmy and his channel.
Yo, Peyton.
I want to make sure we have a good example here recorded on video for those that will be watching later. But it looks like, from what I can tell, you guys are all handling this pretty nicely. So you flip up the denominator first, right? And this will be, even later on when we're dealing with fractions, sometimes this method will be the method. This will be the right way to do it. So Timmy messed up, again, for like the 1,000th time. By what factor did he mess up? The derivative of the inside is 3x squared. He's off by a factor of 3. And so I'm going to multiply by 3, multiply that other factor there. So obviously I have to multiply by 1/3 on the outside to balance that out. Timmy's mistake has been rectified. We're ready to proceed. The 1/3 does not go anywhere. The 3x squared and the dx are both going to go back into the input, which is where they came from. And the only thing we really have to do is find the antiderivative of the big outside function. So it'd be -4th power and then times -1/4 on the outside plus c. And of course, just -1/12. I'm sure you guys can handle stuff like that probably in your head, no problem. That'd be our final answer. And again, if you did this and you thought, man, it seems sort of too easy, how could I check? What do? Do a derivative. Do a chain rule derivative is what it'll end up being, and see if it really does equal your original integrand. Hopefully it will, so you can probably be pretty confident that you did it right. Okay, so yeah, the next one here, I think this is a caution. Yeah, so this is a cautionary tale here. I think I mentioned before that integrands can get really nasty really fast, even with just like a little tiny change. So integrand of sine x, not very hard for you guys. What is the antiderivative of sine x? Negative cosine x. You throw in an x squared instead of just an x, all of a sudden this gets a lot more difficult. Way more difficult, in fact, beyond the scope of our class, other than with power series. We could definitely do this with power series. You'll find that out later. It's not very hard to do. This one right here, you might be tempted to do something like this and say, all right, Timmy, the derivative of the inside, well, that's just 2x, so he's off by a factor of 2x, and then you would say multiply this by 2x, and at this point I've made an error. The fact that I had to change by a variable means that I just have the wrong form. It's not going to be one of these lovely, chain rule mistake type forms. It would be something else entirely. It would certainly not work this way. That make sense? And honestly, if I was supposed to do this at this point, I would just write a power series and integrate that. It would be much easier than trying to figure out what the antiderivative is. I guess we could look it up in a book, or there's probably some website on your computer that has it, but whatever. That makes sense? So don't try to, I don't know that I would say no solution. I would just say I probably would not ask you this question unless I said construct a power series for sine of x squared and then do it that way. But I wouldn't have you just do this. We're going to do power series later. That's a second semester thing.
Cool.
I'm foreshadowing a little bit of what we'll do later on. They are super cool. Can't wait to get there. We'll get there soon. Okay, so also in the video you saw maybe a brief intro into substitution, and we are going to just jump right into the deep end, and we are going to look at one in which you have to use substitution. And that's, I'm just going to tell you right now, number 2, like if with number 2, if you're thinking to yourself, hey, you know what, I'll just use the Timmy messed up the chain rule pattern, and that's just all I'll ever use, it's going to fall flat on number 2. Okay?
It is?
Yeah.
Number 2?
Number 2.
Because the derivative of the inside is only 2.
Oh, shoot.
It appears we have a problem, right?
Gracias.
Dude, what's up?
I had to auditorily view that.
So let's talk about what we can
He's like,
do.
oh my god.
Science.
Oh my goodness.
Well, let's use some use.
So if we're going to substitute, we have to use the letter u. And we're always going to make the u our inside function. If this is going to work, that's how we're going to have to do this. So u would equal what?
2x minus 1.
And if we're going to be substituting, we're always going to have to deal with our du's and our dx's. So what does du equal for this
2dx.
2dx? We're just going to mentally multiply the dx over to the right side. So du equals 2dx. So most folks don't have any problem with this part. Once they kind of get the hang of this and I can substitute and all that stuff, not too hard. But then the difficulty comes in right about here. They'll say the square root of 2x minus 1 could be just u to the 1/2. And they recognize that the dx could be replaced by what? Bless you.
d over 2.
du over 2, yep. So du, and by the way, when I'm doing substitution, when I see I have like du over 2, I usually just write it like this. Du over 2. Just like automatically get it out of there. There's no reason to leave it inside the integrand. But then if you're really honest about this, you've got a major issue because we substituted everything we had to substitute, it appears, and that x has not gone anywhere, right? So can you guys think of a way that we could handle this so that we can substitute without just erasing it or something, the x? What do you think, Nick?
All right, so we have u equals 2x minus 1.
Right?
Then I would add 1 to
Yep.
both sides and then divide it by 2.
Solve for x. That's a great idea. The only thing that relates u with x is that equation that Nick mentioned, and you can just rearrange it to get the x by itself, and this will allow us then to substitute. So I will complete my substitution and get 1/2 times the antiderivative of u plus 1. And again, I'm going to write it like this. I'll write it u plus 1 over 2. So now there's a 1/2 times a 1/2 on the outside. And that's, of course, times u to the 1/2 du. Are we good to go? Are we ready to find the antiderivative?
Wait, why is it not u plus 1/2?
So it's u plus 1 over 2. And I would say that u plus 1 over 2 is the same as 1/2 times u plus 1. So you could have 1/2 u plus 1/2. That would work fine.
Yeah.
But I'm still going to be pulling out any constant multiples I can pull out. I'm going to bring them out.
Okay.
And so I'm just taking this 1/2, which showed up as just a divided by 2. I'm getting that out of there just to uncomplicate my integrand as best I can. You guys never really answered my question. Are we ready to define an antiderivative right here?
Yeah, no,
Not yet. What do we need to do? Yeah, because really you get the integrand of a product, and if you stopped right here and tried to find the antiderivative, you'd find out that Timmy messed up worse than ever, right? He's way off now, similar to how he was at the start. I mean, it's not very good.
It's really sad.
He just cannot get out of his own way sometimes. So we get u to the 3/2 plus u to the 1/2 inside the integrand, just distributed u to the 1/2. Is that okay, Jack? Okay. So then I find my antiderivative by using the power rule. So it'd be 2/5 u to the 5/2 plus 2/3 u to the 3/2 and then plus c. Is that making more sense? Is that good?
No, I was looking at the next one.
Oh, the next one. Oh, yeah, that one does look sort of scary. Okay, so then maybe you multiply the 1/4 in there, so you'd get 1/10. Plugging back in, you'd get 2x minus 1 to the 5/2 plus 2/12, which is 1/6, times 2x minus 1 to the 3/2, and then plus c. So I distributed the 1/4, and then I plugged back in the original expression for u. So don't leave it in terms of u. Make the x expression, whatever it was, in this case 2x minus 1, make that part of your final answer. Okay, so once again, the same principle works. Like if you doubt your substitution, if you think, well, I don't know if the substitution worked, you'd always check this by doing a derivative and seeing what comes up. This one's a little bit harder to kind of reconcile with the original integrand, a little bit tougher because you got the two terms there, but still doable. Okay. Any questions on 2? Now's your chance. Any questions on 2? No? Okay. So 3. So Jack has been looking at 3 for a couple minutes, right? Saying, oh, it looks like a doozy. So let me ask you all a question. We'll hear this, I think. Do you have to use u substitution on number 3. Technically, you don't. You really don't. This is complicated enough to where it may be better, and that's a debatable point. It might be better to use substitution. I can show you, you can definitely do this with just the Timmy messed up the chain rule pattern. What makes this so challenging? Like veterans, do you remember this? We've done stuff like this before.
They're multiplied together.
Okay, but there was multiplication in the other one too. Nick, you said there's multiple somethings?
I mean, like, you have like the 3x, and then the cosine 3x.
And
the
then,
sine 3x squared.
so how many, like to use the terminology I used last year, how many boxes are there? Aren't there 3 boxes?
Yeah.
Oh my gosh, I set another box.
Isn't there like a little tiny box? And then there's like a medium size?
I don't remember how to do this now.
So,
Wait, what?
It's a Russian doll.
Do you have
Where's the
boxes?
third box?
so for those that I didn't have last year, this is how I try to illustrate the chain rule. We just did this in AB. I've got a box, and inside the box, so you open the box, and what's inside? Another box, right? So this is like a composite function, right? Does this make sense? There's a box inside a box. So you open the big box, there's a little box in there. What do you do with the little box? You open it, and then finally there's a little Santa with jelly beans. To me, this is an illustration of the chain rule, right? You got the big outside box, you got the medium-sized box, you got the little box. So, I would say that this is kind of like that. And what we're going to be doing here, as long as we have all this set up right, all we're going to be doing here is taking the little box, putting it back inside the medium box, and then putting that inside the biggest box, and then shutting the big box. That's all we're really doing here, just in an analogous way. So here we go. I'm going to show you the substitution. We can talk about the substitution piece here. And if you want to see the Timmy messed up the chain rule thought process, we can do that too. I think a rewrite is in order. How would you rewrite this to maybe make it as clear as possible what's actually going on with your integrand? Yeah, you've got to use some extra parentheses here, right? So maybe you write it as parentheses, sine of 3x. Whoops. Let's try that again. Double close, squared times cosine of 3x. That's really what that notation means. It's easy to forget or get confused about that, but that's really what it means. So if you do it this way, I kind of like to look at this factor within my integrand, because this is the one that has all the boxes. The other one only has like some of them. So if we thought about this like my little analogy with the boxes, what would you guys say is the little itty-bitty box way on the inside? 3x. That's right. What would you guys say is like the middle-sized box? Sine of, yes, something, in this case 3x. What's the biggest of the boxes? Squared. Something squared. So you can do this a couple different ways. It can be kind of confusing because isn't u supposed to be the inside function?
Yeah.
But technically aren't there like 2 inside functions?
Yeah.
Isn't 3x inside of something else? And then isn't sine of 3x inside something else? So it might be a little confusing as to which one you want to pick to be your official inside, right? I think the medium box makes it easiest. As long as you can handle the chain rule, which I know you can, medium box to me makes sense. So let's try that. So sine of 3x is your medium-sized box, or sine of 3x. We always have to find our du, our differential here. So what would you guys say du for sine of 3x is?
Cosine 3x dx.
Yep, cosine 3x dx times 3. Yep, and we mentally multiply that dx over to that side to help us with our substitution. So now this is where we try to substitute. What could I put in place of my very first factor now that I've set this up?
U.
Not just u, but u squared. So it's u squared. At this point, I don't really have a whole lot I can do with this cosine 3x. I mean, I guess I kind of do. I could do this now. Let's do it like this. I'll change it up a little bit. What if I recognize this? If I just divided by 3, then wouldn't this perfectly match that? So then I could just replace cosine of 3x dx. So again, like Peyton was saying, hey, we did a little bit different order. You could do it this way. If you saw it this way, it's no problem. So cosine 3x dx could be replaced by du. And again, if it's du over 3, I'm just going to write it du over 3 like that. And you got to admit, like, so Jack a few minutes ago was like, that looks like a doozy. Do you see how substitution might be the right choice here? Because we've taken something that really, honestly, did look fairly complicated. I mean, there's a lot going on there. And we have reduced it by substitution down to something that now, pretty simple, right? Substitution might help here. So this would be 1/3 times 1/3 u cubed plus c. And that would lead us to a final antiderivative of 1/9 sine cubed of 3c or 3x plus c. Almost mixed them up there. Okay.
It's like not horrible.
It's not too bad. Not too bad.
Oh my gosh, we literally started singing. Nick, look.
It's another one of those songs that I
This
don't
is
know.
the second class. That
I
people
didn't-
look
I
at.
started that in
You
physics.
started that?
Yeah.
This
Can
is
we
the
sing it
second
as a
class
class?
this year where people.
Not right now.
working on
Put it on
songs.
the
It
video.
took 4 years for.
Maybe at
people
the
to
very
work
end
on
of class, if we have time.
4
I'm
years.
done with
Just
that.
like on the video for Forrest. Just
Poor guy. He's going to be like, what is wrong with those people? What are they singing? Maybe he knows the song. I don't know. Does he know? Forrest. She just wanted to sing some song for Forrest. Okay, final two topics here that have to do with what were our concept for the day.
Oh, jeez, I forgot about this.
Everything we've done has been with indefinite integrals so far. And now the question is, what do we do if there's limits because it's a definite integral?
You have to redo them. Or like,
And
Oh yeah, I forgot about this.
there's plenty of ways to do this, and I'm happy with all the ways as long as you are doing it in a logical, coherent way. There's lots of ways to do this. Maybe we'll try to explore a couple of them. So you can see, of course, that it's one of those composites, and it's a product, and it could be a Timmy messed up the chain rule thing. There's lots of ways to do this. I want to show you guys how you do this with change of variables, which is just another way of saying substitution. That's really all it is. So a lot of this is going to be exactly the same. What would you guys say your u would be here?
x squared plus 1,
Yep, x squared plus 1. How about your du?
2x dx.
Is that making sense? So maybe I come back over here and say, I don't really know what to do with those limits of integration yet, but I do know that I could come over here and say it's going to be the integral or the antiderivative of, it would be u cubed, and then what could I replace the x dx with? Du over 2, right? If you see it over here, you could say du over 2 equals x dx. So wherever you see an x times dx, you could just put a du over 2. So here's my du and my over 2. Would you guys agree with me at this point I've converted everything that needs to be converted over to u's?
Yeah.
I still have my limits to think about, right? So this, what I'm about to write would be a big mistake. If I said, all right, so everything's used, let's just go from 0 to 1 on my integral. We're good to go. What's so wrong with that?
Those are X's.
Those are x's. Don't forget that these definite integrals have their foundation in area. And so when I look at this, this is essentially talking about consider the area between the x-axis and the curve between x equals 0 and x equals 1. And so that 0 and that 1 are x's. And so for me to leave those in there is mixing up x's and u's. We're talking about two different things. We're going to be like off on the graph essentially, right? Because of the way that we've substituted. So we've got to replace the 0 and the 1 with something that does make sense. They need to be in terms of u. No longer should they be in terms of x if we're going to do it this way. So the old low limit was 0. How do you think I could come up with the new high limit in terms of u?
Just like u equals X squared.
Yeah, isn't this the only thing that relates u's and x's?
Yeah.
So if x is 0, u is 1. 0 squared plus 1 is 1. And if x is 1, u is 2. So those are now in terms of u, and now everything officially is converted over to u's. So we'd finish this off by saying 1/2 times 1/4, u to the 4th, evaluated from 1 to 2. And here is the next big trap that people fall right into sometimes. Do you know what it is?
Plugging that one in.
That one. I don't know what you mean by that one.
Why?
Like the number 1?
Yeah, they plug in the one.
Oh, instead of the 2 first?
No, they do what?
I would say at this stage, if I plugged in the 2 and I plugged in the 1 and subtracted, that would be the exact right thing to do. What would be, yeah, people make mistakes here.
They put the X's back in and they don't
I
change the
always wanna
things.
do that.
They do this, they write this, and they leave it like this. What's so wrong with this?
Now you're back to X's again. You switched up the variable.
But what's still a U?
The limits.
Yeah. This is obviously an X expression. These are still U's because you switched them to U's.
You're back to 0 to 1.
Yeah, man.
So if you wanted to, like if you did this and you recognized, oh my gosh, I messed up, you could just go back to 0 and 1 here. That would be fine. That's actually a logical way to do it. That's not a problem. You can choose how you want to handle that. But if I'm going to stay with U's, these need to stay 1s and 2s, and this needs to still be a U. So now this is how it should be. Does that make sense? Okay. So to finish this one off, it would be 1/8 times 2 to the 4th minus 1/8 times 1 to the 4th. 2 to the 4th is 16 over 8 is 2. So 2 minus 1/8, 15 over 8. Sound about right?
Yeah, something like that. We'll go
15 over 8? Okay. Okay. So our final example of the week is number 5. And number 5 is actually a nice illustration as to why you have to still be good at change of variable, no matter which method you want to use. You'll be tested on this concept, and number 5 is a nice way to assess how much you know about changing the variables and substitution. So which of the following is equivalent to that original integral? Got 4 options. See if you can do it. I think that a good way to do this would simply be to try to start the substitution, right? Pretend like it's not a multiple choice and just come over here and say, if I am going to substitute, u would have to be equal to x cubed minus 1. Therefore, du would be 3x squared dx. And then I'm just going to try to plug in and just see what happens here. So I'd have the integral of u to the 7th. And then I look over at my answer options, and they all have u to the 7th, so that didn't really help that much. And then I can replace the dx with du over 3. And this actually does eliminate some options, doesn't it?
It does.
Because the first one doesn't have the 1/3. The last one does not have the 1/3. So we're down to B and C. Comes down to limits of integration. And if you're savvy, you might look at the 1 and 2 and say, ooh, they should be different.
Yeah.
Most of the time, yes. But you might want to just double check to be for sure. My old low limit was 1. So u is equal to 1 cubed minus 1. And this would be where you'd probably confirm this because that's 0. My new low limit is 0, which immediately eliminates B. And hopefully you'd find that the high limit is 2 cubed minus 1, which is 7. And it does match. And at this point, you'd be 100% for sure that the answer is indeed not B, C. I just missed there. Okay, so how'd that go? Questions? Solid. Okay. So when I see you guys again next week on Monday, I guess it is, we're gonna finish pretty easy with this. I would say bring questions. We might actually have a little bit of time to do a little Q&A if those sorts of things come up. We're wrapping up our unit here on Chapter 4's integral stuff. So
Do we need to have Chapter 5's unit packet on Wednesday?
let's see here. Yes, on Wednesday. Yes, for sure on
So
Wednesday.
test on Thursday, I'm assuming?
I got to look at my calendar to be for sure. That sounds right. That sounds right.
When you came to Natalie the next week, it was like a couple weeks ago.
They're going to come pretty fast and furious. Oh, hey, some of you have not turned in your test corrections. If you have yet to do that and you have those with you, you want to do that now. It's in the back there on the top box. I think like 7 or 8 of you have done that. So please do that. I think we're good. Have a wonderful weekend. Enjoy the nice weather. According to the weather